Hello everyone, welcome back to my channel. This is Prabhashi Pereira, and this video is part of my data structures and algorithm series. In the previous videos, we discussed basic sorting concept. So in today's video, we are going to learn one very important non-comparison based sorting algorithm. It is counting sort. Don't worry if you are a beginner or if you have never heard about this algorithm before. I'll explain everything from A to Z step by step in a very simple terms. So let's get started. So this video is about counting sort, which is a sorting algorithm used in data structures and algorithms. We'll understand what it is, how it works, when to use it, and when not to use it, all with examples. Before jumping into counting sort, let's first understand what sorting actually means. Sorting means arranging data in a particular order, usually ascending or descending. For example, arranging marks from lowest to highest, or prices from the cheapest to costliest, or roll numbers in order. Sorting makes data easier to search, analyze, and understand. So that's why sorting is a very important concept in computer science. Now let's talk about counting sort. Counting sort is a non-comparison based sorting algorithm. That means it does not compare elements like bubble sort or merge sort. Instead, it works by counting how many times each value appears in the input array. Because of this approach, counting sort can be very fast but only in specific situations, which we'll see later. Most sorting algorithms compare elements with each other. For example, bubble sort, selection sort, and merge sort compare values again and again. Counting sort is different. It does not compare elements at all. Instead, it uses the value of the elements directly as indexes. This is the main reason why counting sort can be faster than the comparison-based sorting algorithms. Now, when should we use counting sort? Counting sort works best when we are sorting small integers. Example includes exam marks, ages of people, grades, frequency-based data. It is very useful when the range of input value is known and limited. The key idea behind counting sort is very simple. We count how many times each value appears in the input array. Once we know the frequency of each value, we can easily determine the correct position of each element in the sorted array. Because of this, we don't need to comparisons at all. Counting sort works under some important assumptions. First, the input should contain only non-negative integers. Second, we should know the maximum value in the input array. Third, the range of values should be manageable compared to the number of elements. If these assumptions are satisfied, counting sort works very efficiently. So let's clearly state the input constraints. Counting sort works only with non-negative integers and requires a small input range and works best when the maximum value k is close to or smaller than the number of elements n. If the range is very large, counting sort is not a good choice. At a high level, counting sort follows these steps. First, it counts how many times each element appears. Then it calculates positions using cumulative counts. Finally, it places each element directly into its correct position in the output array. Now let's see the exact algorithm. Here are the formal steps of counting sort algorithm. Step 1, find the maximum value in the array. Step 2, create a counting array of size max plus 1. Step 3, store the frequency of each element and then convert the frequency array into a prefix sum array. Step 5, create an output array. And step 6, Traverse the input array from right to left and place elements. Step 7. Copy the output array back to the original array. Now this may sound confusing, so let's understand it using an example. Let's take this example input array. 4, 2, 2, 8, 3, 3, 1. The number of elements is 7 and the maximum value is 8. That means our counting array will have size 9 from index 0 to 8. Now we create the counting array. Each index represents a value from the input array and the number sorted at that index represents how many times it appears. For example, 1 appears once, 2 appears twice, 3 appears twice, 4 appears once, and 8 appears once. All other values appear 0 times. Next, we convert the frequency array into a prefix sum array. Prefix sum means we add the current value with all previous values. This tells us the final position of each element in the sorted array. So now instead of frequencies, we know where each value should be placed. Now we build the output array. We traverse the input array from right to left using the prefix sum values. We place each element in its correct position and decrease the count. Traversing from right to left ensures that counting sort remains stable. The counting array plays a very important role. It stores frequency information and later helps us to calculate positions. Without the counting array, counting sort would not be possible. You might wonder why we go from right to left. This is done to preserve the order of duplicate elements. This property is called stability, and it is very important in many applications. After placing all elements, we get the final sorted array. 1, 2, 2, 3, 3, 4, and 8. As you can see, the array is now sorted in ascending order. A sorting algorithm is called stable if it preserves the relative order of equal elements. Counting sort is a stable sorting algorithm which makes it useful in real-world scenarios where order matters. The time complexity of counting sort is where n is the number of elements and k is the range of input values. This makes counting sort very fast when k is small. Counting sort requires extra space for the counting array and the output array. This is why memory usage is an important factor when choosing counting sort. Counting sort is fast, efficient, and stable. It works in linear time and does not use comparisons. It is excellent for sorting small integer values with limited range. However, counting sort also has limitations. It does not work well with large ranges, negative numbers, or decimal values. It also consumes extra memory, which can be a drawback. Compared to bubble sort, counting sort is much faster. Compared to merge sort, counting sort is more efficient only when the input range is small. So counting sort is not a general purpose sorting algorithm. Counting sort is used in sorting exam marks, ages, survey data, and frequency-based problems. Whenever data is integer-based and has a known range, counting sort can be very useful. You should choose counting sort when the range is small, there are many repeated values, or speed is more important than memory. Otherwise, use comparison-based sorting algorithms. To summarize, counting sort is fast, stable, non-comparison-based sorting algorithm. It works best for small integer ranges but has memory limitations. Understanding counting sort helps you understand more advanced algorithms later. That's it for today's video. I hope this explanation helped you clearly understand counting sort from basics to implementation. Thank you so much for watching, and I'll see you in the next DSA video.